Welcome to the Deep Dive. Our mission is cutting through the noise, finding those really fascinating insights. Today, we're looking at something genuinely groundbreaking in AI, DINOv3 from Meta AI. We're basing this on their recent blog post, DINOv3. Self-supervised learning for vision at unprecedented scale.
Yeah, and what's truly revolutionary here, I think, is how DINOv3 represents, well, a massive leap for computer vision. It's genuinely self-supervised learning for images, sort of like how LLMs learn from text. But the key thing is, it does this without needing human supervision, no manual labeling for these vision models. That really shifts the whole paradigm for visual AI.
That is incredible. Learning without human labels. So when Meta AI talks about a universal vision backbone, what does that actually mean? For organizations dealing with huge amounts of visual data, how does the self-supervision help them make sense of it all?
Well, it means DINOv3 can learn all by itself. It extracts these powerful high-res image features without that really labor-intensive human annotation step. And that drastically cuts down the time the resources usually need for training, which lets it scale up to, 1.7 billion images, models up to 7 billion parameters. It's huge. And this label-free thing, it's critical where annotations are just really scarce or impossible. Think satellite images, complex medical scans, places where labeling is just impractical.
Okay, so it's not just about saving effort on labeling that's big. It sounds like it lowers the barrier for innovation itself. But what really seems to set DINOv3 apart, what makes it potentially groundbreaking, is this idea of a single frozen vision backbone, one that outperforms specialized solutions. Why is that such a big deal for people actually building and using these systems?
Right, that brings up a really important point. Efficiency. And versatility, too. Historically, vision models need lots of fine-tuning for specific tasks. You'd have one for object detection, another for segmentation. DINOv3 gets state-of-the-art results on tough tasks like object detection that's finding what is where in an image. And semantic segmentation, which is like labeling every single pixel, saying this is tree, this is building. And crucially, it does this without needing to fine-tune that core backbone.
Wow, okay. So if I'm getting this right, a single forward pass, just one run of the model, can handle multiple different jobs at the same time, which shares the inference cost, the computing cost. That sounds incredibly efficient. But are there trade-offs? Does this universal approach ever fall short compared to a model built only for one very specific niche thing?
Well, maybe occasionally. You might find a super specialized model gets a tiny edge on a very narrow task it was custom built for. But the source suggests DINOv3 is incredibly robust across a whole range of standard tests. Its real power is that versatility and efficiency. That makes it just ideal for deployment, especially, edge applications, things like drones, smart cameras, robots where processing power is limited. Using one powerful pre-trained model for many tasks. That usually outweighs tiny theoretical gains, especially when you factor in the engineering effort saved.
Yeah, it's easy to admire the tech, but the real proof is always in the real-world impact, isn't it? Are we actually seeing DINOv3 making a difference out there yet? The post mentioned some pretty amazing examples.
Oh, absolutely. We're already seeing tangible results. The World Resources Institute, for example, is using it to monitor deforestation. They've dramatically improved accuracy for measuring tree canopy height in Kenya. Went from like a 4.1 meter error down to just 1.2 meters. That kind of precision can actually help automate climate finance payments. So direct impact on conservation. And we also learned NASA's JPL, they were already using DINOv2, the predecessor, on the Mars rovers, enabling multiple vision tasks with minimal compute power, absolutely critical for space missions.
That deforestation example. Wow. It really makes you think about other environmental monitoring challenges, doesn't it? And it sounds like Meta AI is trying to make this pretty accessible, offering a whole family of models.
Yes, exactly. Based on community feedback, they're releasing smaller versions too, high-performing variants, including different architectures like Connext, just different network designs offering flexibility for different hardware needs. And importantly, they've open-sourced the training code, the pre-trained backbones under a commercial license too. There's even a specific satellite backbone available, plus sample code to help people get started. Open sourcing really pushes things forward.
So let's recap. We've got this universal vision backbone. It's trained at a massive scale without needing human labels. It's outperforming specialized models in many cases. It's incredibly efficient, and it's being made widely accessible. It really feels like it changes the game for how AI can, see and understand the world around us.
Absolutely. The potential here is just incredible. And it really shows how knowledge becomes truly valuable when it's understood and actually applied.
Okay, our deep dive for today ends with this thought for you. Given DINOv3's power to analyze visual data so efficiently across all these diverse, challenging areas, from deep space to deep forests, what new applications, things previously thought impossible, do you think will emerge next?